Hacktex Training Materials. Advanced Textiles Manufacturing Industry. Learning Unit 2. Raw Materials and Products for Functional and Smart Textiles. Lesson 2. Raw Materials for Active Textiles. In this lesson, you will learn about materials for the development of active smart textiles which can both sense and react to environmental conditions, and hence, can be considered both sensors and actuators. The fundamentals of chromo-active materials, phase change materials, shape memory materials, and energy harvesting materials, focused on textile applications, will be revised in this lesson. Chromic responsive materials react to changes on the environmental conditions, providing a color change. The external stimuli that trigger the change can be temperature, electromagnetic radiation, mechanical pressure or deformation, pH, a solvent's polarity, or electric charge, but the most extended for their use in chromo-active textiles are thermochromic and photochromic materials. In textiles, the thermochromic effect is mainly achieved by two approaches: liquid crystals, that are an intrinsic system, and leucodyes, that are an indirect system. Liquid crystals are organic materials remaining in an intermediate state between a solid and a liquid. In that stable state, the molecules of liquid crystals of the cholesteric type present a certain degree of orientation in a helical arrangement. Between layers, the molecule's orientation changes gradually to complete one full helical rotation, defined as the pitch length. When light interacts with the material, the light reflects under a wavelength that depends on the helical structure and its pitch length. But the pitch length is temperature dependent, so the color of the material reveals a color gradient depending on the temperature distribution. Leucodyes base their color change on molecular rearrangements of organic compounds. They are, typically, pH-sensitive dye-based indirect systems, that change pH value due to heating. These systems require the microencapsulation of three components altogether to ensure their interaction: an organic color former, the leucodye, a developer that acts as proton donor, and an organic solvent of low melting point. When heated, the organic solvent melts, allowing a change in the interaction between the color former, leucodye, and the developer, leading often to a color loss. On cooling, the solvent solidifies, and the system reverts to its original state and color. Photochromic textiles present a reversible color change, as a consequence of their interaction with light. In this case, photochromic materials are chemical compounds that change between two forms with different absorption spectra, a thermodynamically stable form A, and an induced form B. The reaction from a form to B form is always triggered by light, but the reverse reaction from B form to A form can be induced by temperature, T-type, or light, P-type. Moreover, photochromic substances can be classified as positive, when the stable form A is colorless, and the induced form B is colored. Or negative, when the stable form A is colored, and the induced form B is colorless. A phase change material, or PCM, is a substance that can store and release thermal energy by changing its physical state, typically from solid to liquid, and back again. In textile solutions, PCMs are commonly microcapsules containing paraffin substances that present this effect at adequate temperature ranges. When a PCM is heated above its melting point, it absorbs heat and changes from solid to liquid, storing thermal energy. When the PCM is cooled below its melting point, it releases heat and changes from liquid back to solid, releasing thermal energy. Due to this, PCM microcapsules applied to textiles provide them a certain thermal regulation. Shape memory alloys base their working principle in their intrinsic ability to endure phase transitions between austenitic and martensitic phases, in favorable temperature ranges. Nickel-titanium alloys are the most widely known shape memory alloys. In the shape memory effect, when the alloy is subjected to a certain stress, the plastic deformation induces this transition, allowing a retention of the deformed shape. However, the induced phase is not stable in these conditions, so it can be reversed by heating. This also releases the plastic deformation retained, recovering the original shape. Due to this, shape memory alloys can be used as actuators in smart textiles. On the other hand, shape memory in polymers is not an intrinsic property, so it requires the programming of a temporary deformed shape. Their most common trigger is also temperature, although there are shape memory polymers that react to light. In this case, we talk about two kinds of segments instead of phases. The hard segments are those capable of retaining the original shape, whereas the soft segments fix the programmed temporary shape by glass transition, crystallization, or reversible bonds. Therefore, shape memory polymers are able to shift from the temporary shape to the original shape when heated, since the soft segments are deactivated so the hard segments can act. Shape memory polymers can be used as actuators in smart textiles. The energy harvesting concept implies the collection of energy that is produced from renewable sources and easily found on our surroundings, such as sunlight, heat, wind, vibrations, pressure, etc. Energy harvesting materials are active materials that respond to external stimuli such as solar radiation, heat, mechanical stress or friction, by converting them into electrical energy. From all those examples, piezoelectric and triboelectric materials present a higher independence of the environmental conditions, so they are an interesting solution for their application in smart textiles. Piezoelectric materials can generate electricity when a mechanical stress, such as pressure, stretch or twist, is applied by the wind, a rainfall, waves, footsteps or body movements, among others. For textile applications, the group of polymeric-based piezoelectrics is of a greater interest, due to their low density and high flexibility. The most known piezopolymer is polyvinylidene fluoride or PVDF. Due to its atomic distribution, PVDF presents electrical dipoles that, with a certain doping and induction, can adopt the beta phase responsible of the piezoelectric effect. This can allow generating sensors for the development of smart textiles. The triboelectric effect occurs at the friction interface between two different materials. To achieve it, the materials have to be widely separated from the triboelectric series, which rank the materials according to their ability to gain or lose electrical charges. Due to the friction, the electrical charges transfer from one material to the other, producing a certain voltage. With this approach it is possible to obtain a triboelectric generator, which can be easily placed in certain areas of smart garments, for energy harvesting. In this lesson you have reviewed the raw materials to generate color response actuators in textiles, focusing on those thermal and light-induced. The phase change materials useful to provide thermal regulation in smart textiles. The shape memory alloys and polymers working principles, that can lead to the production of actuators for smart textile solutions. And the raw materials related to energy harvesting. More specifically, the polymeric piezoelectrics for generation of sensors, and the triboelectric principles to create generators.